What's the best way to pack oranges in a box? Seems easy, right? Just stack them neatly and fill up the gaps. But what if you had to do it perfectly? What if the goal wasn't just to get them to fit, but to prove, mathematically, that no arrangement could ever be more efficient? Now, that's where things get tricky. For over 400 years, this deceptively simple question has kept mathematicians wondering. Even Johannes Kepler, the 17th century astronomer, suspected that the best way to pack spheres was the same way greengrocers stack oranges, pyramid style. But proving that hunch, that turned out to be one of the most stubborn puzzles in mathematical history. The best way to pack spheres was only proven in 3 dimensions, a problem that took computers and years of verification to solve. But in higher dimensions, the best packing methods were a complete enigma. What happens when the simple rules of stacking break down, when intuition no longer works? Mathematics was in dark until Maryna Viazovska cracked the code. This is the story of how a Ukrainian mathematician solved a puzzle that had defied generations of the world's greatest minds, and why her breakthrough isn't just an abstract curiosity. It's changing the way we compress data, protect information, and even understand the fundamental nature of space itself. Let's dive in. Maryna Viazovska was born in Kyiv, Ukraine, in 1984. From an early age, she was drawn to numbers, fascinated by their structure and patterns. She attended the Kyiv Natural Science Lyceum, a specialized school for students excelling in math and science. There she was mentored by Maryna Viazovska, a former research mathematician who introduced her to the beauty of higher mathematics. She competed in mathematical Olympiads, but despite her brilliance, she faced setbacks. In her final year, she ranked 13th in Ukraine, just missing the cut for the country's International Mathematical Olympiad team. But failure didn't discourage her. It fueled her resolve. After earning her bachelor's degree from Taras Shevchenko National University of Kyiv, she pursued advanced studies in Germany and Switzerland. She earned her PhD from the University of Bonn, focusing on modular forms, a key mathematical tool that would later help her revolutionize sphere packing. Sphere packing is exactly what it sounds like, figuring out how to fit spheres together in the most efficient way possible. It's a question that has implications in error-correcting codes, signal processing, and even physics. In 3 dimensions, the best way to stack spheres was proposed by Kepler and later proven by Thomas Hales in 1998. Kepler's conjecture had long suggested that the best way to pack spheres in 3-dimensional space was the familiar pyramid-like arrangement, similar to how oranges are stacked at a grocery store. But proving this mathematically required exhaustive computer verification, leading to one of the most complex proofs in modern mathematics. Hale's proof relied on computer-assisted calculations to check vast numbers of potential arrangements, making it one of the first major proofs to heavily depend on computational verification. But what happens when you take this problem into higher dimensions? Suddenly, intuition breaks down. In 4 dimensions, 5 dimensions, and beyond, the relationships between spheres become far more complex, and the neat rules that govern 3-dimensional packing cease to apply. Brute force computations are no longer feasible, and new mathematical tools are needed to even approach the problem. Mathematicians suspected that the E8 lattice in 8D and the Leach lattice in 24D were the best solutions for sphere packing in their respective dimensions. But what exactly are these lattices, and why do they matter? Imagine arranging marbles on a flat table. The best way to do this is in a hexagonal pattern, where each marble is surrounded by 6 others in a honeycomb-like structure. This same idea works in 3 dimensions, where spheres naturally settle into a pyramid-like stacking, just as oranges are arranged in a grocery store. But when you extend this idea to higher dimensions, things become much more complicated. The simple stacking patterns we see in low dimensions don't work anymore, and instead, intricate mathematical structures emerge. The E8 lattice in 8D is one such structure. It's like a super efficient way of stacking spheres in 8-dimensional space, using a perfectly symmetrical arrangement that minimizes wasted space. Similarly, the Leech lattice in 24D is an even more extraordinary packing method in 24 dimensions. These aren't just random numbers. 8 and 24 are special because they are the only dimensions where these perfect, highly symmetric packing structures exist. These dimensions allow for unique geometric and algebraic relationships that don't appear elsewhere, making them the mathematical sweet spots for sphere packing. Despite strong evidence that these were the best packing solutions, proving it definitively was another story. The missing piece was a mathematical technique that could rule out all other possibilities, and for decades, that piece remained elusive. That's when Maryna Viazovska found a way forward. In 2016, while working at the Berlin Mathematical School, Viazovska made an astonishing discovery. Using an elegant approach based on Fourier analysis, she constructed a function that allowed her to prove that the E8 lattice is the densest sphere packing in 8 dimensions. Her method built upon previous work by Cohn and Elkes, who developed a theoretical framework for proving sphere packing bounds, but they lacked the explicit function needed to complete the proof. Viazovska provided that missing piece. Within a week, she and her collaborators extended the method to 24 dimensions, proving that the Leech lattice provides the optimal packing in that space as well. Her proof wasn't just a solution, it was a masterpiece of mathematical elegance. It was unexpectedly short, fitting into just a few pages, compared to the hundreds of pages and computer verification required for the 3D case. Mathematics isn't just about abstract puzzles, it's about real-world impact, and Viazovska's breakthrough has profound implications across multiple fields. Think about how we send text messages, make phone calls, or stream videos online. Every second, data is being transmitted across the world, but signals are often disrupted by noise, interference from the environment that can corrupt the information. To fix this, we use error-correcting codes which help detect and correct errors in data transmission. Viazovska's work in sphere packing helps refine these codes, making digital communication more efficient and reliable, whether it's for your phone, deep space transmissions, or high-speed internet. Then, there's cryptography, the science of secure communication. In a world where cyber threats are constantly evolving, encryption is crucial to keeping information safe. High-dimensional lattices, like the ones Viazovska studied, play a role in designing encryption systems that are more resistant to attacks, ensuring our personal data remains secure. Her work has indirect implications into quantum computing, a field that is still in its early stages but promises to revolutionize technology. Quantum systems are incredibly delicate, and understanding how particles interact in complex, high-dimensional spaces is essential to advancing this technology. Sphere packing helps describe these interactions, giving researchers new tools to develop more robust quantum algorithms. And finally, we come to theoretical physics. The very structure of our universe may be connected to the kinds of lattices Viazovska studied. The E8 lattice in particular appears in string theory, a framework that attempts to explain the fundamental forces of nature. Her work provides a deeper understanding of these structures, contributing to the mathematical foundations of physics and the mysteries of higher dimensional space-time. Her research isn't just groundbreaking, it's shaping the future of technology and our understanding of the universe. Today, Maryna works at the École Polytechnique Fédérale de Lausanne, EPFL, in Switzerland. She is married to physicist Daniil Ebtushinsky, whom she met during an after-school physics group in her youth. Together, they have 2 children, and she balances the demands of academia with family life. Life took an unexpected turn for her when war broke out in her homeland in February 2022. The Russian invasion of Ukraine placed immense stress on her family, forcing her sisters, nephew, and niece to flee to Switzerland for safety. While she managed to bring some of her loved ones to safety, others, including her parents and grandmother, remained behind in Kyiv. The worry weighed heavily on her, disrupting her ability to focus on research. She has spoken about how difficult it was to work while feeling helpless, knowing her country was under attack. Even in Switzerland, far from the immediate conflict, the war was never out of mind. Yet, through this adversity, she found a renewed sense of purpose, using her platform to raise awareness and support for Ukraine. Winning the Fields Medal is an honor reserved for the most exceptional mathematicians, yet for close to a century it was only won by men. That tradition was first shattered when Maryam Mirzakhani, an Iranian mathematician and professor at Stanford University, became the first woman to win the Fields Medal in 2014. Maryna became only the second woman in history to receive this prestigious award. For her, the recognition is not just a personal triumph, but a symbol of progress in a field where women have long been underrepresented. Mathematics has long been about uncovering hidden structures, and Viazovska's work proves that even in dimensions beyond our imagination, there is order, beauty, and logic. So the next time you see a stack of oranges at the grocery store, remember that proving this arrangement makes the most sense. It wasn't that easy. And thanks to Maryna Viazovska, we're now one step closer to understanding it.